Okay, so my camera ran out of space, and then I had to unload all of the videos from it and put them on my computer. So for you, it's just been an instant. That instant was about 20 minutes. Oh, that's relativity for you. Physics joke. Okay. And then I started doing the lecture again and realized that it was being confused, so I decided just to stop it and start over, so I'm starting over now. Okay, so where we were a moment ago for you guys and half an hour ago for me was as we cool down to lower and lower energies, right, we're going to have more and more particles, more of those bosons sitting close to this ground state where we start seeing the graininess of this, this lattice. So our continuous way of finding this integral is going to break because it's not really an integral anymore. It becomes something discrete. So where we're going to see a phase transition, where we're going to see a difference between the classical physics of a gas and the quantum physics of what we're going to call a Bose-Einstein condensate, will be when this integral breaks. Okay? And it's going to break by this alpha going negative. Right? So right before it goes negative, it's going to be 0. Okay? And so we want to be able to solve this integral for alpha equal to 0. So first what we're going to do is rearrange it. I'm going to rearrange it like this. N equals 2 pi v h cubed 2m k t 3/2. And now an integral which we've done a change of variables on. Okay, so this integral for alpha equals 0 can't be done analytically, but it can be done numerically. And the answer to that numerical integral turns out to be 2.315. So if we want to know at what point this integral breaks, right, we want to know that critical temperature at which this integral breaks and we start seeing new behavior when we get that phase transition, right, that critical temperature. T critical is going to be equal to 2mk, right? So we're just inverting this equation, finding T. H squared 2 pi 2.315 times V times N. 2/3. Okay, so this is the critical temperature. Now if we plug in all the constants for helium, find that its critical temperature is 3.1 Kelvin. So when those people cooled that gas down to 2.17, right? Colder than empty space, that's when they started seeing this new behavior, right? And that phase transition happens at 3.1 Kelvin, right? Just barely above what they were seeing that strange behavior at, okay? So when we cool some gases down, helium-4 included, to this temperature, we create what's called a Bose-Einstein condensate. And in a Bose-Einstein condensate, we have all of those individual particles sharing the same quantum wave function. So we cool them down to the point that most of them are in their ground state, and at this point, the whole gas behaves as a single quantum object, right? You could diffract it like you could a quantum object. You could, if you had two Bose-Einstein condensates and you slammed them into each other, you would see wave patterns arise from their probability waves interfering. Bose-Einstein condensates also have a number of other properties apart from being this kind of weird macroscopic version of a quantum object. In certain cases, they become super fluid, right? Which means that they can flow with no viscosity, right? They don't use energy to flow. And in fact, people have made superfluids, and what they find is if you put, and there's videos of this online you could look up. If you put a superfluid in a container, it'll just flow out of that container. It'll flow up the sides of that container and out. And because liquid always wants to be at the lowest state, it always wants to be on the bottom, so it's going to want to be in this lower energy state in the gravitational field, because that's what stuff in nature wants to do. Normally a liquid couldn't do that because it would take energy to flow, but when this is in this superfluid state with no viscosity, it just flows, right? Because it doesn't take up any energy for it to be able to do that, and it finds this lower state down here. Okay, so by examining the statistics of a quantum gas, we were able to find a new state of matter. Okay, hopefully that was interesting. I'm sorry that this lecture has had a number of hiccups, technical and otherwise. This is one of very few lectures where I just, I'll show you, I just printed out a lot of the stuff from the book and wrote my own notes on it. Not all the lecture notes were like that, but some of them were. And I am not going to do that again because it was a bit difficult to follow, but hopefully this all made sense with the advantages of me being able to pause and collect my thoughts. Unfortunately, this has now been broken up into several videos, so it might be a little more difficult to follow, but hopefully once I get them all uploaded, you can just watch them in a row and you won't notice me having all these technical problems other than me coming on here and being like, oh, I just spent 20 minutes doing whatever. Okay, so as things go on, these classes will get a little better, hopefully. I just received now the whiteboard, so now instead of just writing on a piece of paper and you looking at the back of my hands and thinking, oh, Professor Plix needs to moisturize more, I'll just be writing on a board like normal. Okay, hope you're all doing well. I'll talk to you all soon. Email me if you have any questions, right? If either with this lecture or the previous lecture you didn't understand things, email me that question and then I'll address those at the beginning of the next lecture. Okay, bye everyone, have a good weekend.